The threshold is the membrane potential just sufficient to produce an action potential, just sufficient to get that self-sustaining rise in the membrane potential. So here we have an experiment. It's done in a lab. Don't worry about how it's done. This electrode will change the membrane voltage. This electrode simply measures it, okay? So what this electrode does is it acts like a sodium current. And what it does is it depolarizes the membrane by injecting positive charge into that cell. So it depolarizes that membrane a little bit. So if I depolarize that membrane a little bit with that electrode, my membrane voltage actually becomes less negative a little bit, and then it falls back down to rest. So that was a sub-threshold depolarization. And then I can inject a little bit more positive charge, depolarize it a little bit more, still not enough, falls back to rest. A little bit more, still not enough, didn't open enough sodium channels, it falls back to rest. And now I finally inject enough positive current to hit threshold, and I generate this action potential here. So that is the threshold potential for this nerve, okay? So this demonstrates what happens when you don't hit threshold. You get a little bit of a depolarization, it falls back down. And when you do hit threshold, you generate an action potential through that self-sustaining reaction that I described, okay? Influences on the threshold potential. It is not the same in every cell. It is not the same under all conditions. The potassium and chloride permeability will make a difference here. Potassium always dragging you down toward minus 95, and it will always resist changes in membrane voltage by trying to drag you negative. So you can try to make this membrane more positive by adding positive charge, but it's going to make it much more difficult to get that voltage higher if you've got potassium dragging you back down negative. So it's a tug of war, and with a lot of potassium pulling you down this way, you need a pretty strong force to pull you up. Same thing with chloride. Chloride wants to pull you down. We'll talk about that more in the next lecture, okay? The number of sodium channels. If you have fewer sodium channels, then it makes it very hard to generate an action potential, and you have to depolarize the membrane more and open more of the sodium channels that are available in order to generate an action potential. If you have a bunch of sodium channels that are blocked by, say, a local anesthetic. So if I block a bunch of sodium channels, they can't open. So if I have 100 sodium channels, and I have to open 20 to get an action potential, then if I block half of those sodium channels and make the total number 50, then that means I still have to open 20. But now I'm opening 20 of 50, which is 40% of the sodium channels, rather than 20 of 100, which is only 20%. And the only way to open 40% is to raise the voltage more, which means I have to get to a higher voltage and open more activation gates before I'll hit threshold and generate that self-sustaining reaction, okay? So more sodium channels, your threshold potential is lower and it's easier to fire an action potential. Fewer sodium channels like a local anesthetic, or in the case of resting inactivation with hyperkalemia, then you have to get to a higher threshold. You have to depolarize the membrane more. The rate of depolarization actually makes a difference. To make a long story short, your activation gates open quickly, your inactivation gates open slowly. And the trick is to depolarize that membrane really fast so you open a bunch of activation gates without closing a whole bunch of inactivation gates. If you raise that voltage slowly, then yeah, you'll open the activation gates, but you'll also give the inactivation gates time to close. And the trick is to get it to the point where both of those gates are open. The inactivation gate hasn't had time to close, and the activation gate is open. And the faster you depolarize that membrane, the more channels like this, where both gates are open, you're going to find, okay? And so the threshold potential is lower, and it's easier to fire an action potential if you depolarize the membrane quicker and get what sodium channels you do activate, and you do open activation gates with, to not have their inactivation gates have time to close. The quicker that voltage goes up, the easier it is to open this without closing this, and the fewer channels you actually have to open to get sodium to flow across. The fewer activation gates you have to actually open. And what that means, bottom line, is you don't have to depolarize as much if you do it really fast. And the trick is to get the channels in this configuration, okay? And if you do it faster, you'll get more like this. And that lowers the threshold, okay? So we talked about action potential propagation earlier in the lecture, and we talked about this unidirectional propagation and the fact that the propagation has to be unidirectional because the membrane becomes refractory back in this area where the action potential has already traveled through. So there's only one direction for that action potential to propagate. It's toward the membrane that is still at rest and still ready to be depolarized and ready to fire an action potential, not refractory, okay? Things that affect the speed of propagation, the bigger the cell diameter, the more rapid the propagation. I won't go into why that is. It's got to do with cable theory, and it will not make you better doctors to understand why. Just know that it is. Bigger diameter, more action potential propagation. That is relevant, however. That fact is relevant because neurons tend to be really big cells. And now you know why. They propagate action potentials. They're specialized to do that. And if you want a cell that's specialized to propagate action potentials, you want one that's got a big diameter, okay? So big cells, generally speaking, propagate action potentials rapidly. Your excitable tissues tend to be big. Your muscle cells are big, okay? And your nerves are big, that's why. Resting membrane resistance, all that means is permeability to potassium and chloride. If I have more open potassium channels, then that makes it hard to depolarize that membrane, and it's going to slow action potential propagation. It's going to make it harder for this action potential to propagate in this direction because it makes it harder for this little bit of charge that's moving under this patch of membrane to depolarize that membrane enough to generate another action potential. So there's a delay there, and it slows the action potential when you have a lot of open potassium channels and a lot of open chloride channels. So the lower the resting membrane resistance, that is, the more open potassium channels and chloride channels you have, the higher the conductance for those ions is, the higher the permeability is, the slower the action potential conduction. Conductance is the inverse of resistance. So we're talking about low resistance and high conductance slows your action potential propagation. That is relevant. We'll talk about why in a minute. Intracellular longitudinal resistance really isn't terribly relevant. It's the ease with which charges move longitudinally along this membrane. So I think you can see that the easier this charge moves to underneath this little patch of membrane, the easier it is going to be to depolarize that membrane and for the action potential to propagate. The truth of the matter is that the intracellular resistance doesn't vary in cells, but effectively it varies in cells that are hooked up by gap junctions, and that means cardiac myocytes. So the more open gap junctions you have, the lower the longitudinal resistance, and the fewer open gap junctions you have, the greater the longitudinal resistance. And so more longitudinal resistance, slower action potential propagation. Relevant really to the heart more than anything else, okay? The number of sodium channels. If I block sodium channels, it's going to slow the action potential propagation. Because in order to depolarize this, basically I just said, it raises the threshold and it makes it harder to fire an action potential. That means it makes it harder for this charge just underneath this patch of membrane to get this patch of membrane to fire. And that slows the action potential down, all right? So fewer sodium channels or sodium channel blockade slows the action potential conductions, okay? And finally, the membrane capacitance, okay? The lower the capacitance, the faster the action potential propagation. The higher the capacitance, the slower the action potential propagation, which is why we still teach it, okay? So one way to measure the rate at which an action potential propagates is to do an experiment like the one that you see at the top of this page, where you depolarize a patch of membrane to some sub-threshold point, okay? And you generate what's called an electrotonic potential, which just means submembrane potential. And that membrane potential propagates down this ion, but it's not an action potential because as it propagates, it decrements. And it usually finally decrements to 0. And the faster it decrements, the slower the propagation. This equation, which appears on boards, which is the only reason I'm giving it to you, describes this experiment. And the voltage that's generated at any given point away from this point here, the initial generation point. Okay? What that voltage is tells you how quick the action potential is propagating. If it's high, it's propagating quickly. If it's low, it's propagating slowly. This length constant is what's relevant. The larger the length constant, the faster the action potential propagation. And the length constant is calculated with that equation, which I do not expect you to memorize, but you should know the relationships. Because what it does is it quantifies a lot of the things that I just listed on the last slide. Large length constant, fast propagation. A stands for fiber diameter. Fiber diameter goes up, propagation rate goes up. Membrane resistance. As membrane resistance goes up, that means fewer open potassium and chloride channels in that membrane. The larger the length constant and the faster the propagation. In our denominator, we have the longitudinal resistance, okay? If that is high, then it slows propagation. High resistance there, low length constant, slow propagation. And so a lot of the terms are terms that we talked about on the last slide. It quantifies them. Scientists like that, physicians who do research like that, and sometimes that means physicians that write questions for board exams like it, which is why it's there, okay? Very quickly, I know they go over this in histo, but we have myelinated nerve fibers. I want to talk about this because it's why we teach capacitance, basically. Myelination takes place when Schwann cells or oligodendrites wrap themselves in the form of myelin around these nerves. And the areas where you wrap the nerve in myelin with these, the oligodendrites are in the CNS and the Schwann cells are in the periphery. The myelin-covered section is the internode, and the uncovered section is called the node of Ranvier, okay? The myelin increases the effective membrane thickness, decreases the capacitance, and so it makes it very easy to propagate an action potential where the myelin is, okay? Decreased capacitance, a very rapid action potential. In this case, you can see you're thickening that membrane a lot, effectively, okay? There are also fewer sodium and potassium channels and channels of all types underneath that membrane, and even the ones that are there, they have a very hard time conducting ions with myelin wrapped over them. So there is a very high resting membrane resistance as well. Those things combine to make that area, the propagation of the action potential in that area, very rapid, okay? And what happens is your action potential is basically generated where the nodes of Ranvier are, because that's where your sodium and potassium channels are. And then, just underneath the membrane where the myelin is, the action potential propagation is so fast that the action potential appears to jump. That's how quick it is. and it'll jump this millimeter or so to the next node of Ranvier where it slows down again, where you activate sodium channels and potassium channels and regenerate some the action potential there. And then they jump again because this area propagates the action potential so quickly. We call that saltatory conduction, okay? And it makes conduction through myelinated nerve fibers extremely rapid. Go ahead.
Can you quickly review why decreasing conductance makes action potential propagation go faster?
Yes, what we're talking about is resting membrane resistance. Potassium channels and chloride drag you down. So the fewer open channels for potassium and chloride you have, the less they're dragging you down and the easier it is to depolarize a membrane, and it makes that action potential conduction extremely fast. Okay?